So basically, obviously the point of this discussion is to compare and contrast the keto diet versus the carnivore diet. I also want to talk at some length about the obsession, I guess, with ketones that many of the ketogenic pundits seem to hold and espouse, perpetuate and carry on. So we'll be dealing with that and talking about the process of ketogenesis itself, what it is, why it happens, why some of the ideas that are held out there are not great in terms of why people think it happens and what its physiological meaning is, really, I guess. And so, yeah, that's the point of today's lesson. So we're going to have some learning outcomes so that you all know what the focuses or foci, I suppose, are for the course. It's very important that we do remain focused on these, I guess, during the discussion. And so at the beginning of each of these sessions from the course, there will be, a listing of the learning outcomes. So obviously what we want to do is describe the production of ketones. How does it happen metabolically? What are the reactions involved? What are the enzymes involved? What goes on there at that level? We want to explain why ketones are produced as best we can. From a physiological point of view, it's all very well to look at what the metabolic reactions are, what the molecules look like, what the enzymes are, etc., which we will do, obviously, in outcome 1. But outcome 2 dives a bit deeper and says, well, okay, great, this is how we make ketones. Why do we do it? What is the physiological meaning of it? Why does this go on? I want to talk about some of the proposed benefits of ketones in and of themselves. There are a lot of people running around saying ketones are good for you because ketones are, for example, anti-inflammatory and blah, blah, blah. I'll talk about sort of a list of proposed, either tested or otherwise, theories regarding whether ketones in and of themselves have benefits just by virtue of being in your blood, floating around, I guess. And indeed, I'm going to talk about some of the potential pitfalls of ketones in and of themselves as a sort of counterpoint to the proposed benefits, and indeed look at some of the ideas held and espoused by some of the pundits in that area as well. So we'll be doing that. I want to discuss at some length the apparent obsession held by people that promote ketogenesis and ketone-based exogenous diets and indeed ketogenic diets and all these kind of people that are running around the internet and elsewhere telling us, that the production of ketones is a good thing. We should be producing ketones all the time. We should absolutely avoid anything that kicks us out of ketogenesis. We should use the urine sticks. We should, keep an eye on, are we still in ketosis, and etc., etc., etc. I want to talk about that because there's a lot of misinformation there. There's a lot of potentially dangerous misinformation being espoused and spread there. By those individuals. Thank you very much for that, whoever that is with the noisy motorcycle outside. And so, yeah, I want to cover why it is that those things are not necessarily such good ideas at all. We do need to make a clear differentiation between normal, metabolically induced, dietarily induced ketosis, and we need to make it clear that that's not the same thing as a thing called ketoacidosis, which is a pathological derangement of the pH, which occurs in uncontrolled diabetes, not in the normal metabolic ketosis at all. I want to differentiate ketogenic diet from carnivore diet in terms of what is the intent of each of those diets. What are the practices? What is done? What is it that, what are the differences? And that will give you an idea of I guess which one of those dietary approaches is potentially the most sensible one to to pursue. Also, I want to have a look at a particular genetic single mutation that is prevalent in a particular population of humans, those being the Inuit, who have lived above the Arctic Circle for a number of generations now, and there is a particular genetic mutation in that population which is very, very prevalent and does vastly reduce those individuals' ability to produce ketones, to enter ketosis. And so there are, a number of pundits, one in particular, going around saying that's clear evidence that ketogenesis is a bad thing, and it's a reason why we shouldn't even look at ketogenic diets, etc., etc., etc. So I want to cover what that particular individual is saying, why it is he's saying it, and why it is that he's completely wrong in respect to what he's saying. So that will be covered in this presentation as well. So, by way of getting into those outcomes, buckle up. It should be fun, hopefully. It should be a deeper dive into the area of ketogenic diets, ketone production, ketogenesis than perhaps you're used to. That's a good thing, I think. I think we need to understand what we're talking about when we talk about this area. And so, I am going to take my time and work through this in quite a sort of conversational way if I can. Please do feel free to post questions after the video, and those of you that are watching on the YouTube channel can post those questions underneath the video in the relevant spot there. Those of you who are watching in the course proper, obviously you will have your specific means by which you can contact either Pim or myself or both of us for further advice as part of your membership as studentship to this course. So please do feel free to get back to us and ask for any clarifications you need to, irrespective of which format it is that you're watching this particular video in. So with that said, let's crack into it. The first thing that we need to understand, and understand clearly, is that metabolism overall has two kind of gears in terms of energy storage. We have a very, very limited ability to store energy in the form of a carbohydrate, that being glycogen, in our muscles and indeed in the liver to some extent. We really don't store a lot of energy at all in the form of carbohydrate. It's mainly stored in the form of fats, fatty acids. So our metabolism basically has two gears in terms of providing us ongoingly with energy, and those two gears are anabolic and catabolic in nature. So the anabolic side of the functioning of the metabolic system is in the build-up of fatty acids. If you have an energy substrate surplus at a given time, say immediately after eating, or indeed, in the case of various other things that can occur that we'll talk about a little bit today. So excess energy substrates will lead to the build-up, the running of the gearbox in that direction. There will be the storage of energy in the form of fats. Pretty simple, really. When energy is required and there aren't a lot of energy substrates floating around, we need to provide them from the storage form. The storage form is in the form of the fats, as I said, so we're going to basically run the gearbox in reverse. We're going to break down fatty acids to provide those energy substrates. It being kind of like a gearbox, you can't run a gearbox in forward gear and in reverse gear at the same time. That's not possible. The same is true of your metabolic pathway. It is either anabolic or it is catabolic. It is either building up fats in the terms of when there's an excess, or it's breaking them down when energy is required. So that's the first thing to understand. It's vital to understand that clearly. It is a gearbox. it will run in one direction or the other, but not both directions at the same time. It does take quite some time to change the momentum of the metabolic system from reverse to forward or from forward to reverse. It's not like just putting in a clutch and moving a gear shifter. It does take longer than that. You do need to slow it down to a halt and then start running it back the other direction. There is an inertia involved. It does take time. You need to understand that as well. Okay. So basically, yep, that's what we're saying. You cannot build up and break down fatty acids at the same time. You're doing one or the other, basically. Largely, among other things, one of the most potent controllers of the direction in which the gearbox is running is the intake of carbohydrates in the diet. When you consume any significant amount of carbohydrate-rich foods in your diet, that will necessarily predispose you to being in fat storage mode. It's that simple. There will be an excess of energy substrates available in the blood as a result of the intake of those carbohydrates that will put you into fat storage mode. Be aware of it, basically. The way that the carb intake or an amount of carb in your blood has an effect on which way the metabolism runs is via an effect where citrate will pull in the cells when you have a lot of blood glucose, which is what happens when you eat carbohydrates. You get an increase in the blood glucose. That leads through a bunch of reactions, this knocking on, leading to this, leading to that. It leads to a build-up of citrate and AMP kinase. And basically, those things have an effect on the concentration. When you see something in square brackets like that, it means concentration of. So the citrate and the AMP kinase, or adenosine monophosphate kinase if you like, they have an effect directly on the Malonyl coenzyme A concentration in the cytosol of the cell. And basically the Malonyl coenzyme A is the kind of control lever that talks about fat buildup versus the breakdown of fat. If you increase the concentration of Malonyl coenzyme A, you are committing the metabolic pathway to the build-up pathway. So when you eat carbs, that's why you get fat, basically, because it causes your body to go into fat storage mode via a very direct, very chemical, very allosteric course of events. That's what it is, basically, in short. So, yeah, citrate, in other words, will directly up-regulate the acetyl coenzyme A carboxylase enzyme, which is the one responsible for the production of malonyl coenzyme A. So that leads to an increase in the concentration of malonyl coenzyme A, and it's that which the malonyl coenzyme A is at that point committed to the build-up of triglycerides, fats, basically. If there is a lowering in the adenosine monophosphate kinase concentration, that also leads to an increase in the concentration of malonyl coenzyme A. One of the ways that you will get a decrease in adenosine monophosphate concentration is by having a surplus of acetyl coenzyme A molecules floating around in the cell, which is what you get when you have a raised level of citrate as a result of the intake of the carbohydrates in the diet, basically. So, yeah, the intake of carbohydrates will cause an increase in citrate. An increase in citrate causes an increase in malonyl coenzyme A. The intake of carbohydrates also directly causes a decrease in AMPK concentration, which has the same synergistic effect of increasing the Malonyl coenzyme A. So that leads to the buildup of fats. Cool. How does that work? Basically, it works because Malonyl coenzyme A directly down-regulates another membrane-bound enzyme in the mitochondria. It happens to be called CPT1A, and basically the CPT1A enzyme is responsible for transporting free fatty acids from the cell cytosol into the mitochondrial matrix, where it is broken down to acetyl coenzyme A through the process of beta oxidation, and then that runs the tricarboxylic acid cycle, otherwise known as the TCA cycle, otherwise known as the Krebs cycle, which produces all our energy. In other words, an increase in Malonyl coenzyme A in the cell cytosol prevents the mitochondria from being able to import fatty acids, thus committing those Malonyl coenzyme A's and acetyl coenzyme A's from which they are made to the fat storage mode and not to the energy usage mode. In other words, the carbohydrates are mandated to use carbohydrates for energy rather than fats. It's a lock and key, one or the other. We can't do both at once. Either you're oxidizing primarily fats or you're oxidizing primarily carbohydrates. And in any given sort of tissues, whether that be your muscles or your heart or your brain or wherever they are really, in the liver, it's a lock and key thing. It's we're going to do one or the other. So yeah, that's basically how that works. So as we've said, the production of Malonyl coenzyme A, with that preamble out of the way, so basically the preamble says, okay, if you increase Malonyl coenzyme A, then your energy is going towards fat storage. It's not being oxidized. We'll just wait for Mr. Noisy. Good work, good work. I wish my one was that big. Anyway, there you go. So an increase in Malonyl coenzyme A leads to one metabolic pathway being activated and the other one being turned off. So how do we produce this Malonyl coenzyme A? Well, as we've said, when we intake a lot of carbohydrate, that increases the level of citrate in the mitochondria as a direct effect of the way that all the intermediaries of the tricarboxylic acid cycle occur. So we get this increase in the citrate concentration, which is basically it's an allosterically controlled phenomenon, if you like to think of it that way. Basically, the citrate is then exported from the matrix of the mitochondria out into the cell cytosol. There's an enzyme called ATP citrate lyase, which produces acetyl coenzyme A from the citrate in the cytosol. The acetyl coenzyme A carboxylase then forms Malonyl coenzyme A from that, and that's what we're looking at in that grey box over there at the bottom of the screen there. Okay, so we have an acetyl coenzyme A molecule here as produced by acetyl coenzyme A carboxylase from citrate in the cytosol. We have a bicarbonate ion which is floating around in the cell cytosol as part of that reaction, plus we have some energy input from ATP. The acetyl coenzyme A carboxylase then acts on that and we form a Malonyl coenzyme A, and obviously as a result we get an ADP plus an inorganic phosphate as a result of that. So that's the production of Malonyl coenzyme A, and as we said, the Malonyl coenzyme A directly then inhibits the intake of free fatty acids from the cell cytosol into the mitochondria. That locks those fatty acids out of the oxidative pathway, thus committing them absolutely to fat storage. Okay, so that's pretty straightforward. And that's what we're saying there, that Malonyl coenzyme A directly blockades the CPT1A enzyme, which is embedded in the cell membranes in the mitochondria. Okay, so that's how carbohydrates basically cause fat storage. That's the exact mechanism of it. It is an energy level controlled phenomenon, because it is actually the level of citrate and therefore acetyl coenzyme A in the cell cytosol that controls that switch. But it is specifically carbohydrate intake that causes that increase in citrate concentration in a way that leads to that cascade of events. So that's when you hear people say, the reason that we go into fat storage mode is because of carbohydrate intake. That's the reason they say that largely. That's the underpinnings of it. From there, let's slightly switch directions and let's talk a bit now about the production of ketones. Basically, the production of ketones that occurs in hepatic mitochondria, in other words, those mitochondria that live in the liver. Basically, the CPT1A enzyme imports free fatty acids into the mitochondria, and a process of beta oxidation occurs. The result of the beta oxidation process is the provision of a number of molecules of acetyl coenzyme A, which you will see here at the top of this chart. Here we see 2 molecules of acetyl coenzyme A. And then down here there's a third molecule of acetyl coenzyme A. So we get 2 molecules of acetyl coenzyme A plus a coenzyme A molecule being spit out there. So one of those comes away, the SH coenzyme A, that comes away. We condense 2 molecules of acetyl coenzyme A together at this step, and then at this step here a third molecule of acetyl coenzyme A is added, and we get a spitting out of the coenzyme A, SH, from there, and we end up with a new molecule, which is basically the condensation of 3 molecules of acetyl coenzyme A into 1 molecule, and that molecule is called beta-hydroxy beta-methylglutarol coenzyme A, which is sometimes referred to as HMG coenzyme A. Now, anyone that follows my channel at all should now go, that's interesting, isn't it, boys and girls? Because that'll be familiar to anyone that's listened to any of my videos on my YouTube channel. Those that are doing this course that haven't seen my channel, perhaps not so much so, perhaps you do know what it is. Anywho, I shall put you out of your misery if you don't know and tell you. Beta-hydroxy beta-methylglutarol coenzyme A, whoa, that's a mouthful, that's why they call it HMG, I suppose. That is the first precursor intermediary in a series of reactions which lead directly to the cellular metabolic production of our good friend cholesterol. So basically, when your liver goes into beta oxidation overdrive mode, and we'll talk about why it happens soon, that overdrive of beta oxidation provides a lot of acetyl coenzyme A into the cell. A lot of it is condensed into beta-hydroxy beta-methylglutarol coenzyme A, in other words HMG coenzyme A. Some of that HMG coenzyme A then goes down one pathway and produces what we call ketone bodies. Okay, and those are acetyl. The acetyl coenzyme A comes off there, and we get acetate, and acetoacetate is then via the input of a bit of energy in the form of an NADH cofactor, then produces beta hydroxybutyrate, or BHB, and then sometimes we get a spontaneous evolution of acetone, which is a decarboxylation reaction there. So when you smell the ketone breath, what you're smelling is acetone, basically, which is a volatile, will easily turn into gas. So you can breathe it out of your blood. That's kind of a loss, if you like, an insensible, they call it an insensible loss of carbon skeleton in the form of acetone. Beta hydroxybutyrate is still useful in the body. It's not volatile. You don't breathe it out. It doesn't bubble out of your blood. It remains in your blood. It goes around to other cells in the body, most notably the brain, the heart tissue, and skeletal muscles can all use ketones as a source of acetyl coenzyme A, which is the first intermediary of the TCA cycle. So basically what I'm saying is that BHB is an energy source, and so the reason that we produce ketones at all, the first reason that comes out of all of this, is that coenzyme A is a quite large molecule. It can't be imported and exported from the cells. It's a big, massive thing. So what we need to do is get the coenzyme A's off it, and that's what happens through this series of reactions, and allows the production of these ketone bodies, which are much smaller. They can pass through the cell membranes, they can be exported to the blood and exported around the body for use as an energy source. Obviously, when the blood glucose level is high because of the intake of carbohydrates, then we have the funneling of coenzyme A's into the production of what we spoke about earlier, the Malonyl coenzyme A there, and that circumvents this course of events. When the blood glucose drops lower, then this course of events goes into play. It's one or the other again. It's the energy provision is the control lever, and then so that's what causes the production of the ketone bodies. So as I said, some of the HMG coenzyme A goes that way, ketone bodies. The rest of it goes the other way and produces, you guessed it, boys and girls, cholesterol. So a lot of people will say, yes, I went on a low carbohydrate or ketogenic diet and my cholesterol went up. Well, that's why. There you go. It's normal, it's natural, it's nothing to be concerned about. Cholesterol is not involved in heart disease in the way many so-called experts will tell you that it is. I'll be covering that in some depth here in this course in another lesson. I've also already covered it in quite some depth on my YouTube channel for those that want to go and have a look at that. Basically, that's a pseudoscientific load of crack pottery. Cholesterol does not cause heart disease. Cholesterol is a very vital, very needed substance in your body. Your body generates it itself. You can see here that it does that. It does that as part of the normal natural functioning of metabolism. You can't live without it. To say that it causes heart disease, it's just rubbish. So as I say, I cover that in another area, in another fora, so go and have a look at that. So basically, to finish off that discussion there, that's what we get in this metabolic pathway here. Two acetyl coenzyme A's condense together. One of the coenzyme A's comes off it. That forms acetyl coenzyme A. Then we have the addition of a third molecule of acetyl coenzyme A. The coenzyme A is spit off as part of that condensation reaction. That makes HMG coenzyme A. then that goes either off, let's say, this direction over here somewhere to make cholesterol, or if it's not making cholesterol, then the acetyl coenzyme A is taken off it. That gives us acetoacetate, and then there's another reaction that forms that into beta hydroxybutyrate and a spontaneous evolution of the more volatile acetone, which therefore means that substrate there is lost. It's either urinated out or breathed out, and that's basically where that one goes. So that is the production of ketone bodies metabolically. That's how it happens. So the next question therefore becomes, well, why? Why do we make ketones? I've kind of covered the first reason already, and that is to say these coenzyme A molecules that are just shown here as a CoA is actually this great big convoluted, it's a very large molecule. It will not pass cell membranes. You can't import and export it from the cell. It remains in the cell, and it does its work in the cell as a cofactor to these reactions, as an enzyme functioning sort of cofactor, if you like. That's why it's called a coenzyme. So if we need to produce a bunch of acetyl coenzyme A in tissues around the body where the blood glucose level is dropping, we don't have blood glucose to top up the glucose. We need to get coenzyme A into those cells for energy in another form. And so the two ways that your body does that is by generating glucose from non-glucose sources in a process called gluconeogenesis. And also the other way it does it in a more rapid way is it produces ketone bodies, which can then go through the blood, diffuse out to the cells that need the glucose elsewhere in the body, and they can enter those cells and then be reunited with coenzyme A and used as an acetyl coenzyme A. Basically, it's a way of keeping the energy flowing in that sense. That's kind of why it happens. The reason that's necessary is that because some of the tissues elsewhere in your body, other than in the liver, where ketone bodies are made in the liver, other tissues are not able to use fats to produce acetyl coenzyme A. They can't undertake beta oxidation. An example of a tissue that can't do that is brain tissue. Your brain needs to run on glucose or on ketone bodies, basically. So the result is that your hepatic or your liver tissue acts as a currency converter, if you like. So it's either storing fats when there's a lot of energy around in the form of acetyl coenzyme A's, either as a result of carbohydrate intake or sufficient, energy provision from whatever source, really. And when there's not sufficient blood glucose because there hasn't been enough gluconeogenesis, there hasn't been an intake recently of carb in the diet, then the liver will start to produce ketones to sort of top up, I guess. It's like an overdraft. Moving on to the benefits of ketones. Perhaps actually before I do that, I should talk a little bit more about the levels to which the production of ketones contributes to, for example, the running of your brain. In a normal ketogenic diet set up in healthy individuals who don't have uncontrolled type 1 diabetes, in other words, normal metabolically induced ketogenesis, normal dietary induced ketogenesis, typically that leads to a buildup of ketones in the blood over however long you're in a ketogenic diet. You would struggle even in deep ketogenesis of that kind to have a concentration in the blood of ketones over somewhere between 3 and 5 millimoles per litre. In deep ketosis, that's when that keto stick, that urinalysis stick, goes deep purple. That's between 3 and 5 millimoles per litre. That amount of ketones in your blood will provide about 15, 16, 17% of the total energy requirements of your brain. Okay, so what we're saying is, even in deep dietary ketosis, 80 up to 85% of the energy that your brain is using on a minute by minute basis is still in the form of glucose. And that glucose is being produced by your liver in parallel to its production of ketone bodies. That glucose is being produced from non-glucose sources, for example, usually fats, and sometimes if you've got very, very limited fat available, then as a final option, then protein is used basically, but your protein stores are pretty well protected. So you're generally producing, there are exceptions to that. There are some particular amino acids which are gluconeogenic by nature and do encourage it. I'm just talking about an overall picture here just to get an idea. So what I'm saying is that 85% of your energy when you're in deep ketosis is still coming from glucose. It's just that glucose is being generated by your body from fats. Okay. So that said, this whole idea that you need to stay in ketosis at all costs is fundamentally ridiculous. Okay, you are not going to supply more than about 15% of your brain's energy from ketones. Your ability to produce energy is uncompromised because you are still making glucose via gluconeogenesis, which means you are still using fat, which means you are still stripping fat off your body, which is the goal of the ketogenic diet. The problem here is that people don't understand this metabolic system very well. They think that ketones are completely replacing carbohydrate sources of energy in the brain. That's not what's happening at all. They think that if they shut off their ketosis, that means they are no longer using fat, and we should therefore avoid getting kicked out of ketosis or going out of ketosis at all costs, which means we limit our protein intake, because protein, some of it, as I said, is gluconeogenic, and if we have too much glucose in our blood from either consuming it or from body's production of it, that's going to shut down ketogenesis, and we don't want to cut down ketogenesis because we think the only way to use fat is via ketogenesis. It's not. We can use it by gluconeogenesis as well. This obsession with being in ketosis all the time is nonsensical. It's garbage. It's nonsense. You don't need to be in ketosis all the time to lose fat off your body using a very low carbohydrate in the diet approach nutritionally. It still works fine without being in ketosis. That said, also, secondly, the keto stick's idea of urinating on a urinalysis stick and having a look at the colour of the swatch and going, oh, I'm in ketosis, I'm a good boy or I'm a good girl. Look, all you have to do to get your ketone level in your urine down very, very low so that it won't register on that stick, even if you are in deep metabolic ketosis, all you have to do is some intense exercise for an hour or two before you do the urinalysis, and then you go wee on sick, oh, I've got no ketones, and you think you're failing. Nonsense, boys and girls. It's not scientifically based. It's fad based. It's something that's being sold to you by people with something to sell you. Urinalysis sticks. The idea that ketogenesis is the magic thing that you need to be doing. Ketogenesis is not the magic thing you need to be doing. Ketogenesis is the magic thing your body does naturally to provide quickly some energy to tide you over in between meals when your blood glucose drops, because getting the wheels rolling for gluconeogenesis is a slower process. We need to have an overdraft. It's ketones, okay? That's how it works. Those are the interactions of the systems of ketogenesis and gluconeogenesis and energy provision at large. The goal of a ketogenic diet for most people that undertake a ketogenic diet is to lose fat. Okay, the goal of the ketogenic diet is not to produce ketones. I hope I've made that clear. Okay, that said, there are some proposed benefits of ketones per se, of having ketones in your blood. There is some research that suggests that it can be useful. Ketones have been shown to be an anti-inflammatory agent. That's a good thing. We don't want to be chronically inflamed. When you have an energy deficiency in your body, one of the things that will necessarily cause is inflammation. So obviously, one of the reasons that ketones are produced by your body is to counteract that chronically. In case you don't get food reasonably quickly, you don't want to be chronically inflamed. Your body doesn't want to be chronically inflamed. So this is a switch it uses to counteract that. It's a control loop. So that's another reason why our body makes ketones, obviously. Ketones are antioxidants. They do counteract the effects of oxygen-free radicals and things. That's a good thing. Ketones will cause your appetite to go down directly, and also as a secondary, there's another secondary reason for that, and that is that ketones actually will slow down your metabolic rate, because when there are ketones being produced, it means that gluconeogenesis isn't up to speed at this stage, and so we need to slow down our energy metabolism while the ketones are around, to give everything a chance to get up to speed. That's why you want to be in ketosis transiently as required when your blood glucose is dropping. That's why you don't want to be in ketosis all the time, because it will slow down your metabolism chronically. That leads to chronic inflammation. The antioxidant, anti-inflammatory effects of ketones will start to wear off. Your body's ability to generate ketones drops as a function of time in ketosis. Not so good. Another benefit of ketones is mental clarity, focus, and alertness. Your brain actually prefers running on ketones to glucose. It's more energetically favorable. It's a known effect that you get this clarity, this focus, this alertness, this sort of sense of euphoria while ketones are around. It gives you a sense of having energy when actually energy is limited in terms of your blood glucose. As well. So those are some of the effects, basically. There's a bunch of others as well. I mean, you can go and do your own research on this if you want to. Look at PubMed or Google Scholar or whatever search engine you like to use. There's a bunch of different researchers proposing a bunch of different sort of beneficial effects of ketones. There's even a group of people who, funnily enough, have something to sell you, that being, a ketone supplement, that are suggesting that if you actually consume exogenous ketones, in other words, ketones from outside your body in the form of a powder that you put in a drink, shake, and you drink that's a good thing. I don't buy it myself, but there are people talking about some of the benefits of ketones just purely because they are ketones. Okay, fine. That said, there are some pitfalls potentially of ketones as well. As I've mentioned, the reduced basal metabolic rate, the effect on thyroid function if you are in ketosis constantly, that can be a bad thing. If you're cycling in and out of ketosis normally on a daily basis, as you should do, the thing that should cycle you out of ketosis is your meal. Your meal should contain animal fats and associated animal protein, the flesh and fat of animals. Okay, that will produce the energy you require for the next 24 hours if you're eating once a day, or 12 hours if you're eating twice a day, sort of thing. And when that energy starts to drop away because it's being used and your blood glucose starts to drop, then ketogenesis kicks in as a short-term overdraft, while gluconeogenesis then kicks in after that to maintain a stable energy provision for your brain and heart and skeletal muscle tissues and things. That's what you want, a normal cycling. That's That's the goal, not being in ketosis all the time. That's a bad thing, most likely. There is at least one pundit, which I referred to at the beginning of this chat, who is online talking about being in ketogenesis, dietary ketogenesis all the time as a bad thing because of ketoacidosis, he says. I'm talking about Chris Master John, who has a PhD in, I think it's biochemistry or something or other. Anyway, his whole bag in terms of this particular argument is that people who are in ketosis all the time will develop acidosis. I'm sorry, Chris, it's nonsense. As I said, the concentration of ketones in the blood at peak, deep, dietary, normal ketogenesis struggles to get much above 5 millimoles per litre. That absolutely will not result in a derangement of pH in the blood or anywhere else. It's just nonsense. Ketoacidosis occurs at sort of 15 to 20 millimoles per litre of ketones. The only way you can get 15 to 20 millimoles per litre of ketones in your blood is if you have uncontrolled diabetes mellitus. Okay? It does not occur to a normally healthy population with normal metabolisms. It's just simply not a good argument, Chris. I'm sorry, but it's just nonsense. Diabetic ketoacidosis and normal dietary metabolic ketosis, not the same thing, not the same ramifications. The conflation there is completely inappropriate. No, basically. So as I said, ketosis does not subserve more than about 15, 16, 17% of brain energy needs, depending on which papers you read. Gluconeogenesis does the rest. It's only in keto, it's only when you have uncontrolled diabetes where the brain cells are unable to take up the glucose that the ketones build up and build up and build up and build up to that level. And plus you also get with those people the toxic effects of glucose, because glucose in your blood is toxic, and the more glucose you have in the blood, the more toxic it becomes. So that's how that one works. So this obsession with ketones, the whole idea of calling a low carbohydrate diet a ketogenic diet is, in my opinion, what is to blame for people latching onto the term keto and the concept of ketogenesis as being the thing it's all that it's about, and they are now obsessed with the process of ketogenesis, and they think ketogenesis is the thing that's netting them the benefit. No, ketogenesis is a necessary part of the integrated functioning of our metabolic systems, which is a short-term overdraft energy supply methodology by which our liver can control the provision of energy to our tissues, most notably our brain, in terms of its ability, or its inability, I should say, to use glucose-based sources for energy. Fat. So your brain's inability to use fat for energy, get that right. And so therefore that's the methodology while we're waiting for gluconeogenesis to kick into play. That's what it's for. It's a short-term cycle in and out of overdraft facility. It's not a long-term loan. It should not be used as such. We should not be obsessed with ketones. We should not be weeing on sticks. We shouldn't even be looking at our blood ketones. It's ridiculous. It's nonsensical. It's a fad. It's a thing being sold to you by people who have something to sell you. The problem with these ketogenic diets is that the production of ketones becomes the goal, rather than being correctly viewed as a transient consequence of the low carbohydrate intake in the diet. The goal of the diet is to get fat off your body, or some people use ketogenic diets for other purposes, like the control of uncontrolled epileptic seizures and things. You can look through the literature for yourself and see those kind of things. But for most people who undertake a ketogenic diet, the goal is to lose fat off your body, not to produce ketones, and that's where people have got this wrong. There is no really convincing reason to suggest that ketones in the blood are a desirable thing in and of themselves, other than the ones I spoke about that are kind of, there is some inference in the literature that says, yeah, it might be good to have them around because as part of holistic functioning, as part of being in ketosis, they do play roles. For example, the anti-inflammatory role, that's why it might be handy to have them around, that kind of thing. And the obsession with keto and ketogenesis and weeing on sticks and all that kind of stuff is a pseudoscientific cult. It's not sensible, it's not helpful. That's not the kind of diet we need to be following. So that said, let's compare ketogenic ketosis with ketoacidosis, just to make this absolutely clear. Ketosis, normal, natural, indicated human function. It's the way that we control energy provision to our brain in between meals. It's a short-term natural overdraft cycle in and out of thing. Ketones in our blood should range between 0.3 and about 5 at maximum millimoles per litre. At maximum deep ketosis, you're going to subserve about 15% of your brain's energy needs, not much more than that. There is no derangement to the pH of any of your fluid compartments or cells or tissues in your body whatsoever. That's absolute nonsense, Chris. It occurs normally and naturally, as I say. It's transient, not chronic. It also probably acts as a second messenger hormone to the hormone system. It probably acts in down-regulating basal metabolic rate while gluconeogenesis comes up. You want that happening acutely as and when it's needed. You don't want that happening chronically. That's not a good thing. So that's ketosis in a nutshell. Ketoacidosis as a different thing. That's a derangement of the system where the production of ketones goes up and up and up and up and up because of the inability of the brain tissues and other tissues to absorb glucose from the blood and get energy. The build-up of the carbohydrates, because they can't be got into the cells, that causes the blockade of the fat metabolism as well. The cells are starving, so we need to produce ketones more and more and more and more, so you get 15, 20 and upwards millimoles per litre of ketones. That leads to a pH derangement. That's a consequence of uncontrolled diabetes mellitus. It doesn't happen in normally functioning, otherwise healthy human individuals. It's a chronic condition, and it's definitely absolutely contraindicated. You don't want that happening whatsoever. But let's not conflate those two things, Chris Master John. They're not the same thing at all. Even if you are chronically in normal ketosis, that's not a good thing for a number of reasons, but it's not going to cause acidic derangement. It's going to cause slowing down of the metabolic rate. It's going to cause adverse effect on your thyroid functioning if you're in ketosis all the time and you're not cycling in and out with a sensible diet. So that's that one. So keto diets versus the carnivore diet. In a ketogenic diet, unfortunately, for most, the goal becomes ketogenesis itself, which is, as you say, if you understood this lecture, you'll understand why that's fundamentally, contraindicated, a bad idea, ridiculous. You don't want to be doing that. The method to producing ketogenesis is in severely limiting the carb intake. Usually it's less than 20 grams per day. Sometimes it's less than 50 grams per day, depending. It's a severely limited amount of carb intake. But also at the same time, proponents of the ketogenic diet tell their devotees to also severely limit the amount of protein that they intake, because protein can be gluconeogenic and that will shut off your ketosis. Well, it's supposed to do that. That's the whole point. It's another way of producing glucose for energy. Why would you want to shut it off? Because the reason is because you think ketogenesis is the goal. It's not the goal. The goal is to lose fat. Okay. misinformation, bad information, the wrong thing to do. You absolutely should keep your protein intake up. My particular way of describing this is that in terms of calories taken in, your diet should ideally be 50-50 protein and animal fat, animal protein and animal fat that is, and actually 0 carbohydrates, 0 plants. So the difference there is that on the carnivore diet, the goal is the elimination of plant matter from the diet, not the elimination of carbs. Okay, plant matter is carb-based, so in eliminating all the plants, you eliminate most of the carbs from the diet. As such, you actually achieve a ketogenic, what's usually called a ketogenic diet anyway, because your carb intake will usually be less than the 20 to 50 grams per day that is required on a ketogenic diet. In the carnivore diet, the method is the same as the goal. The goal is remove plants. The method is remove the plants. So, self-serving, that's good. The outcome goal is reduced inflammation, reduced autoimmune problems, reduced digestive problems, reduced psychological issues, etc. All of these issues are directly attributable to the intake of plant materials. I describe the reasons why that is so in other lessons in this course and also in other videos that I have produced for my YouTube channel for those that are watching in that forum. So please do have a really good look around my YouTube channel, and for those of you who are in this course, you can also look around my YouTube channel as well, of course, but you should also look to the course materials contained within this this package that we've put together, Pim and I, this marvelous course that we are running. So those are the differences there. I hope you can see that one of those is a clear, sensible methodology, and one is a pseudoscientific bunch of crack pottery, pretty much. I wanted to talk finally about this particular group of genetically distinct individuals in the Inuit populations. Some people call them Eskimos. Apparently that's not a good term for them. So apparently it's Inuit. They are the peoples that live above the Arctic Circle, in the northern parts of Canada and Greenland and those kind of areas. As it turns out, up to 80% of individuals in that population, or those distinct populations around the globe at those latitudes, have a heterozygous expression of a particular single nucleotide polymorphism, or a SNP, or a genetic mutation, basically. And what this mutation causes is a vast reduction in the production of the enzymes involved in ketogenesis. These people are much less able to produce ketones. It turns out to be one of the most powerful selective sweeps known in human genetics. A selective sweep is a gene which becomes almost ubiquitous in a population because it is selected for as a positive thing. So what we're saying is the fact that these Inuit are vastly compromised in their ability to produce ketones, there is clearly a survival benefit in knocking that ability down. It is good for those people in that environment for some reason. At least one pundit, I'm talking about Chris Masterjohn, claims that it's good to knock down the ability to be in ketosis because of pH derangement. I've covered that already, Chris. Sorry, mate. No, just frankly, not a good idea at all. I think it's more likely because of the downregulation of the BMR, the effect on the thyroid functioning, some other effects tied in with light and frequency of light that's available to those folks, being different to what we've got at latitudes closer to the equator. It's an overall picture. It's not really well understood as to exactly why this is a good thing. Chris's idea is one idea. As I said, I don't think it's a very good idea. I think it's nothing to do with that at all, because there's nothing to support Chris's idea. I'm not saying there's more supporting different ideas. I'm saying we really just don't know. All we know is that it clearly is good in those populations of people consuming that degree of carnivorous diet at that latitude on the planet is a good thing for those people. That's why it's selected for. So yeah, there are many reasons why it might be a good thing. We really don't know much about it. More research is required. I think we need to look into that one more carefully, and I certainly myself am keeping an eye on the literature in that area to see what does come out of that, if anything, and I will let you know if anything obvious does come out of it.